Welcome back. This is part two of the lesson on motion and forces. And in this video, we're going to take a look back at Newton's second law and take a deeper dive with the F equals ma equation, including looking at some scenarios, and we're going to do some calculations. And we're also going to get into the idea of multiple forces on an object and this idea of net force in this video. And in order to really visualize some of this, this PhET lab online through colorado.edu is phenomenal. This is a great resource, and the PhET labs in general are going to be a great resource for us in this module. So the first thing we're going to do is use the acceleration feature in this online lab. And you see you have the scenario set up. You have other masses that you can add, different, we're going to check masses here on these features up here. You can see the different masses, right? Right, we're also going to want to see the values for acceleration, and that means we're going to click acceleration. Notice the bar it gives you here. So we can now use this, and also friction. We're going to put friction down to nothing here. So we're just worrying about the one specific force going in. It's going to be going in the rightward direction here, the applied force from our orange friend here. All right, so we're going to try to look at this and see how this F equals ma thing works. Does force equal mass times acceleration? What happens when we change those variables? And that's going to help us just to understand this a little bit better. So we have a 50 kilogram mass. Our acceleration is of course 0 right now because we are at rest. As soon as we begin to apply force, you're going to see this begin to go in the right direction, and some things are going to change. And I'm going to pause it pretty quick so we can lock in some numbers. So let's go with 200 newtons to start of applied force. Notice 200 newtons, rightward direction as our vector, 50 kilogram mass. Let's pause it. It's starting to move at a quicker pace here. And notice our acceleration, 4 meters per second squared. All right, so we got some values, and we can check if this all matches up. Well, how do we do that? Well, with the equation from Newton's second law, of course, F equals ma. So we can check this out to just confirm that this equation holds true in the scenario we just ran. And if we look at our picture to the right there, we see the applied force was 200 newtons, and that's going to be on that side. And you have the mass of 50 kilograms times the acceleration, which over here was 4 meters per second squared. And that, of course, checks out. 50 times 4 is 200. And 200 newtons is the same as 200 kilogram times meter over second squared. All right, so this definitely checks out. We see how Newton's equation can be used to calculate force, can calculate mass, acceleration, any of those three, as long as you know a couple of them. Of course, here we are just confirming the equation with all numbers. But let's take a look at what would happen if we change something. Now we can of course look at this in many different ways, right? We could consider increasing the force with the same mass, seeing what that does to the acceleration. We could look at increasing the mass and seeing what that could do, or seeing if the same mass can move at the same acceleration and what would the force be. So let's go ahead and try. Let's see, we got F equals ma. And let's say we increase the force. Let's say we increase the mass here. And instead of 50 kilograms, we wanted to move this refrigerator, 200 kilograms. But here's the thing. We want to maintain that same acceleration. So the new question would be, what kind of force do we need to put behind this to move a 200 kilogram mass? So let's check it out. All right, so we're going to do force is equal to the new mass of 200 kilograms times the acceleration that we know we want to keep, 4 meters per second squared. And of course here we're going to do this 200 times 4, which gives us 800 kilograms times meters per second squared, or just 800 newtons. So we see, right, that an increased mass, right, so mass goes up, the force goes up. Okay, so we got to notice that there's a direct relationship there. As you increase mass, the force that you're going to require to move that mass at a certain acceleration, of course, is going to go up at a constant acceleration. Okay, so let's reset and do one more, and let's think about calculating a possible new acceleration with this new mass. So we're going to go with, of course, our equation, F equals ma. And we're going to look for a new acceleration. Pretend that one's not there. And we're going to say that we're going to move this fridge again, but we're going to use the same force that we had originally. And that's 200 newtons. So we have 200 newtons is equal to the mass of 200 kilograms, this refrigerator, times the acceleration. All right, and then we, of course, just solve for A. And how we're going to do that, we're going to divide by 200 kilograms, divide by 200 kilograms over here. 200 divided by 200, that of course is equal to 1. So our acceleration is now going to equal 1.00. We'll do it just how they give us to it in the simulation, meters per second squared. All right, so what do we see? What is the relationship between these? Well, as mass increases with a constant force, acceleration we see goes down. So an inverse relationship there between mass and acceleration. And, that makes sense. Increased mass, more stuff to move, right? The acceleration is going to be a little slower at a constant force. If we decrease the mass here, of course, less force, or if you have the same force, you're going to increase the acceleration. All right, so now we're able to see just F equals ma, the intricate relationship between these different variables when we're talking about forces. All right, now we can jump back into this simulation here, and we can begin to look at a few new ideas regarding forces, one of them being friction. And of course, friction is the resistance an object will encounter when moving across another object or surface. All right, so we're going to be able to see that here. So you see, this is the friction simulation. So you have friction right in the middle. We're just going to leave it where it's set. Okay, we have our 50 kilogram mass again. We have our guy here who's going to be doing the work. And I've checked these boxes here so we can see the sum of forces and the mass. Let's go with our original force number. That was 200 newtons. So if we jump up, we're going to quickly see motion start, but we're going to see something a little different. Okay, we're going to see what happens when friction is involved. So let's jump to 200 newtons. All right, so we get moving, and notice here, all right, we have our applied force. I'm going to pause it, of 200 newtons. We have our mass of 50 kilograms. Now, without friction before, the acceleration was 4 meters per second squared. That was with no friction. That's of course going to change now, because notice here you have a friction force of 94 newtons. That is this surface here exerting a force against this crate in the other direction of the applied force. Okay, and this brings up the idea of a net force on an object. All right, you see, or sum of forces, same thing, net force. Here, with the 94 newtons into account, has to be subtracted from the applied force, because notice the directional difference, and we'll get back into that. But we have a net force of 106 newtons going in the right direction here. Okay, so again, 200 newtons going to the right, applied force thanks to this guy. Friction force going in the opposite direction to the left. Notice this vector arrow of 94 newtons. You subtract the two to get our grand total of 106 newtons as the net force on this 50 kilogram mass. So another way that we can view this idea of net force on an object, all right, we can draw a little picture. It's something called a free body diagram. So let's say we had our, our ground here. We had our crate. We can say that's 50 kilograms still. That's fine. Let's say that we are going to apply a force of, let's say, 100 newtons in this direction. All right, but the surface here is going to exert friction on this crate, and we're going to say that it's 20 newtons in that direction. Now, notice how I drew my arrows, right? Not exactly to scale, but this 100 Newton arrow is much larger, all right, than the 20 Newton arrow going in the other direction, just to kind of visualize that size difference of these forces, okay? The magnitude is different here. Remember, we said anytime you're dealing with forces and these vectors, you have the direction, and you also have the magnitude. You have to have the amount. All right, so what would the net force here be? We have 100 newtons in one direction. You got friction going against that applied force of 20 newtons. So all you need to do here is subtract the net to find the net force. So we have 100 newtons minus the 20 newtons. that's going to give us a net force of 80 newtons. So the net force on that 50 kilogram crate is 80 newtons. Knowing that, then we could calculate acceleration. You could go ahead and plug it into F equals ma. If we know that the net force is 80 newtons, the mass is 50 kilograms, you can now calculate the acceleration of this crate, even with friction, into account. All right, so let's do another one. We have this surface here. Say we have the same kind of box or crate. We can even say that it's 1 kilogram. Okay. We're going to apply a force. We're going to try to move it in this direction. Let's say we apply a force of 70 newtons. Okay. And the frictional force is still going to have us go in the opposite direction. It's going to be 20 newtons. Excuse the writing there. So net force on this object at this given time is going to be 50 newtons, right? We just did the 70 minus 20. So the net force would be 50 newtons in this direction, or we can even call this the positive direction right now, because that's the direction we want to go in. Now, just for frame of reference sake, all right, frame of reference is very important in physics. To know, this is the positive. I call it the positive direction only because that's the direction I want it to go in. Right? Now, if a person came along and started pushing in the opposite direction, right, and they started pushing against my box this way with a force of 100 newtons, well, now they just overwhelmed the force that I was pushing, 70 newtons, and you're going in the opposite direction. And so we call that a negative net force, but only because I've established that I want to go in the rightward direction instead of the left, whereas this new force is going to left. So that's just kind of the idea of frame of reference here. And frame of reference is very important in physics, like I said, because what if I all of a sudden took this flat surface where I said it was the ground, and now I said that it is a table, and this is the ground down here? Well, does that change things? You might say, well, no, I'm still pushing 70 newtons, and there's still friction, of course. Okay. Yeah, but there's new forces going on here. What is the main one that we're going to be talking about? This box is now off the ground. It's elevated on this table. So, you ever heard of this thing called gravity? Right? So the force of gravity is going to be pulling this box down, or we could say that's its weight. The weight of the box is important. It's about a 10 factor here when you're talking about the mass of something versus its weight. So this is going to be, let's say, 10 newtons in the downward direction. Okay, but it's not going down, is it? It's not getting pulled to the ground. The gravity's pulling on the object. But what's stopping it? Well, you have the table here. The table is exerting a force upon that object there. And that is something called the normal force. Right? Normal force. Let me just change colors and write that up here for you. Normal force. That is opposing the force of gravity pulling something down. The normal force is always perpendicular, right, to the surface that the object is upon. All right, so the normal force, again, is opposing equally. So the normal force here is going to be 10 newtons, right, when you compare it with the force of gravity or the weight of that object. So this is a free body diagram that's including an applied force, a frictional force, you have the force of gravity, and you have the normal forces. So this is big in physics and with motion because you have to think about the sum of all forces on an object. You can't just, you can isolate one, of course, in a controlled environment, but in the natural world of motion, all right, there's going to be multiple forces acting on an object at all times. All right, sometimes it'll be balanced, sometimes it will be unbalanced. And to help us look at the difference between balanced and unbalanced forces, we come back to our PhET simulation, the net force portion of this PhET. And it's pretty intuitive, right? The balanced and unbalanced. Hopefully you're thinking the word equal in there, right? And where that would apply. But this simulation is going to really help you, especially when you go through this module and the assessment for this module. So let's try this out. Let's just throw this blue person up here. All right. You see there's a left force of 50 newtons. Sum of forces, 50 newtons in the left direction. Well, this would be unbalanced, right? Well, if we hit go, we can see that. It's only going the wrong direction. All right? The forces on this object, the crate of candy, not balanced. How do we do a balance? Well, let's add a red person in. Oh, now we have 50 newtons going in the right direction. Notice the sum of forces equal. What's going to happen? Nothing. No motion. Nothing's going to happen. If we reset it, and let's say we add one of these big people. Holy moly. Now we have, again, unbalanced forces. You have 200 newtons in the left direction, only 50 newtons in the right direction. All right, 150 newtons going in the left direction. That's the sum. That's the net force. And you'll notice, of course, they're going to go flying in that direction. This poor red person's like, what did I get myself into? Blue wins, of course. Okay. Well, how do we bring this back to balance? Well, we have to equal it out. So how can we do that? I mean, of course, could we add this red person? Sure. Let's try something different, though. Let's see, we got this medium person, and we still have 50 newtons going in the left direction. Let's see what happens if we add this person. There we go. So even with 3 people on this side and 2 over here, the number of people might be unbalanced, but the forces they're exerting are balanced. So if we go, they're all going to pull, and the forces are equal. Therefore, we have a balanced scenario now here. Okay, so balanced versus unbalanced forces. Think about that. All right, so in this part 2 video for module 1, we have thrown a lot at you, including Newton's second law, of course, the equation derived from it, force equals mass times acceleration. We've seen some of the natural relationships that come out of that, especially that inverse relationship between mass and acceleration. We've also looked at the idea of friction and net force on an object, which includes, of course, you got gravity in there and the normal force that can be exerted on an object from another object. And we also took a look at the idea of balanced and unbalanced forces. All right, so a lot in there. If you need more practice, please go to the resource page built in. All right, you can, of course, access the PhET lab yourself. Give it some practice to really work with these variables and these multiple forces. All right, and practice using the documents that you have here. You have something for everything: motion and forces, weight and mass, and F equals ma problems, normal force problems. Okay, so check those out. Practice up, and we'll see you in the next video.